Bam! Mr. True. In this lesson, we are going to learn about even and odd functions. You want to learn how to do this because it can quicken, speed up the process of graphing functions, especially higher order polynomials, which are very, very tedious. If you can identify the function you're graphing as even, then you can only graph half the function and then just mirror it over the y-axis to get the other half of the graph. Identifying even and odd functions can also become useful when you get into calculus and you start integrating functions. That can be a tedious process as well, and identifying that it's one of these two types of functions, even or odd, can speed up that process. Even functions are symmetric to the y-axis, and the test is f of negative x, or the opposite of x, is equal to f of x. I might say that is negative sometimes. I really need to emphasize that it's the opposite value. I don't really know what the value of x is. If x is negative, then the opposite of a negative number is actually positive. So really I should be saying that, you know, the test is when you plug in opposite values, you get the same answer. These are the same names on both sides, and there's no, there's not a 2 here and a 1 there, so we're getting the same answer. That's what algebraically that says. Graphically, it is like this parabola that we have here, y is equal to x squared. When you plug in opposite values, you get, again, the same answer. So like negative 3 squared is 9, and positive 3 squared is 9. So you have this reflection, this symmetry over the y-axis, and you get that graphically by the fact that we have again the same y value but opposite x's. So I just mentioned symmetry to the y-axis. When we get to odd functions, I'll be talking about symmetry to the origin. What you will not hear me talk about, other than the fact that it's incorrect, is symmetry to the x-axis. We were talking about even and odd functions. A function, something where every single element in the domain, or every independent value, or every x value, if you want to get less technical about it, is only matched up with one y. If we're saying independent, one domain value. If we're saying domain, x, one x to one y, one independent value to one dependent value. Wasn't sure if I said that right. And every one element in the domain is matched up to to only one element in the range. So I'm saying the same thing with different vocabulary. So if you have an equation that's symmetric to the x-axis, that means that it would fail the vertical line test. When you drop a vertical line representing an x value, if it can cross more than once, well, it's not a function, it's a relation. So we're not talking about types of relations, we're talking about types of functions. Thus we will, other than right now where I'm saying it's incorrect, we are not going to be talking about symmetric or symmetry to the x-axis. So we have some 5 examples here which I want to discuss with you and how to algebraically check whether they're even or odd. If you have a graphing or allowed to use a graphing utility, of course you can graph it and just see that symmetry to the y-axis, but graphing utilities cannot show holes in the graph. They can just sometimes be a little bit misleading. So we'd like to be able to check algebraically. If we have y is equal to x squared, then we can take this, plug in the opposite of x, and get that negative x times negative x. See, I'm saying negative again. Those two negatives, or those two opposite signs, are going to cancel each other out, and we're going to get x squared, because when you multiply like bases, you add those exponents. Please note that I wrapped that in parentheses. Every time you do substitution, you should be putting parentheses around where any of your variables used to be, so that you can get your signs correct, or maybe even apply the distributive property correctly if you happen to have substituted in an expression. Because if I had wrote negative x squared, well, the only thing that power of 2 is acting on without parentheses is the x, and that would be negative x times x, which is negative x squared, which of course, I mean, we can have functions that are even or not even, but that in this particular case is an incorrect answer, starting from here and substituting in the opposite of x. Okay, I need to harp on that all the time with my students because they always forget to use parentheses when they substitute. We have y is equal to the absolute value of x. Now, if you know what that what we call parent function looks like, then you'll already know that this is an even function. It's basically kind of like a V with the sharp bend on the origin. It's at 0, 0 because, or it's at the x value of 0 because the x value of 0 makes the expression inside the absolute value symbol equal to 0. That's where your sharp bends occur in absolute value graphs. And algebraically, though, how you again test with this notation of plug in the opposite of x, well, this becomes y is equal to the absolute value of the opposite of x, which you can think of as the absolute value of -1 times x, and we can take care of the absolute value of that -1 and just say that the answer again is simply the absolute value of x. So the absolute value of -x is still going to be x, just like we started off with, so thus that is an even function. Now, cautionary note here, if there are two terms in that absolute value equation or function, then you can't just sort of like, we do, the absolute value symbols tell us it's a function which tells us how far a value is away from 0 on the number line. That kind of gets shortcutted into, it just gets rid of the negative sign. The absolute value of -5 is 5. Well, that's true, but when you have two or more terms in your algebraic expression that's inside that function, looking at that and going, oh, well, that's just 2x plus 7. That is not a correct answer. When I looked at this -x and I showed that the absolute value of -x was the same as the absolute value of positive x, well, for one thing, there was only one term inside that absolute value function, not two. Now, we could factor a -1 out. Now, I'm not going to take that -1 and just sort of like let it pull out of the absolute value symbol. They look like parentheses, but parentheses are just a grouping symbol, an absolute value function that they're actually doing something. Again, they're telling you how far a value is away from 0 on the number line. So I can't pull the -1 out front. That would be absolutely a wrong answer, but I can recognize that with all of this written as one single term, that the absolute value symbols will take care of that that factor of -1 out front and leave that -2x plus 7 inside the absolute value sign. And these are, if you graph these, going to be equivalent or equal the same graph. So absolute values can be a bit more tricky than most of these other functions we deal with in our algebraic studies. Okay. So you can't just cancel out the negatives when there's more than one term, and you cannot factor out a negative and bring it out in front of an absolute value symbol. Now here we have just a polynomial, y is equal to x to the 4th plus 3x squared. It's a polynomial because there's only one independent variable and all of the exponents are positive integers. And identifying even and odd polynomials is pretty simple too. If all the exponents are even, it's even, and if all the exponents are odd, then it's going to be an odd function, even though we haven't talked about odd functions yet. But again, applying the test, it's going to be y is equal to the opposite of x raised to the 4th plus 3 times the opposite of x raised to the even power of 2. And again, if you have just a bunch of pairs of negatives, right? Negative times negative is positive. And so if you have a bunch of pairs of 2, they're going to cancel out, and this becomes, I'm running out of space here, x to the 4th plus 3x squared. So far, everything we've looked at has been an even function. Now, what if I brought this out and said, well, this is my problem. When I plugged in my opposite expression for x, well, this even power would take care of that negative. But here, there's 3 of those negatives. So the first two will cancel out to make a positive answer, but then you bring in that one last negative sign and we'd be negative 3x to the third power. This new expression is not exactly the same as what we started with, so it is not an even function. And again, we haven't gotten to the odd ones yet, but it's not going to be an odd function either. These are kind of special cases. Not most equations or functions are not going to be even or odd. But if we can identify when they are, again, we can save ourselves some time. So we can certainly have a situation where it's neither even nor odd. Now here, we have y is equal to the the square root of 4 times negative x to the second power plus 3. And again, that opposite of x, that kind of negative x being raised to an even power, that even power is going to cancel out that negative, giving us an equivalent expression or the same expression back of the square root of 4x squared plus 3. And thus we plugged in the opposite of x and we got the same expression back. So this was even as well. Okay, now for our last one here, I don't know if you've studied in any trig yet or not. If you have, then you probably already know what the cosine graph looks like, and you already know that this is an even function. If you've not taken trig yet, but you're allowed to use your calculator, then I would just basically suggest with this kind of question here, you're kind of stuck with just testing some points. And don't do just one, but try the cosine of, well, you're probably working in degrees. So try the cosine of 30 degrees and the cosine of negative 30 degrees and see if you get the same answer. And by the way, now I know what's called a unit circle. Again, I'm not sure if you've studied that yet. So I know what the exact value answer is. I'm not sure what the decimal approximation is. But the cosine of 30 positive rotations are counterclockwise from the positive side of the x-axis, and negative 30 is negative 30. Negative rotation is in a clockwise rotation from the positive side of the x-axis. So the cosine of 30 and the cosine of negative 30, that's going to be the square root of 3 over 2. Again, whatever decimal approximation your calculator gives you, as long as it's in degree mode. And if you try the cosine of 30 and negative 30, the cosine of 45 and negative 45, the cosine of 60 and negative 60, you're going to continue to get the same answer over and over and over again. And thus the cosine function is an even function as well. Okay, so that is about all I can talk about for even functions. Let's get on to the odd ones. Odd functions. Well, they are symmetric to the origin. And the test for odd functions is that when you plug in opposite values, you get the opposite answer. So we have an equation here, we have a graph, and let's just say that's the equation of y is equal to x cubed. Well, if you say put in negative 2 to the third power, negative 2 times negative 2 is positive 4, times negative 2 is negative 8. And if you plug in positive 2, 2 times 2 is 4, times 2 is 8. So I've plugged in two opposite numbers, negative 2 and positive 2, and got out opposite answers. And so that is an example graphically of what your function may look like, or will look like, if it is odd. Now, we say that odd functions are symmetric to the origin. You can think of this in two different ways. You can see it as a rotation of 180 degrees of rotation about the origin, or you can think of it as two reflections, where we take this portion of the graph and we reflect it over the x-axis, which is going to give you, that would be, well, we kind of talked about that already, symmetry to the x-axis, even though it's not really a function, where you'd have the same x value but getting the opposite y value. So if you reflected this point over the x-axis, you'd be down here at x negative y. And then you do a second reflection where you take that and you reflect it over the y-axis, and you end up with your opposite x, opposite y, or negative x, negative y. So you can think of it again as two reflections, one reflection being over the x-axis, and then a second reflection taking that over the y-axis, finally landing you at the point negative x, negative y, because when you reflect over the y-axis, like we talked about in the previous screen, you'll change the sign of the x-coordinate. Okay, I like to focus on the fact that you can take this and rotate it 180 degrees and have the graph perfectly line up on itself, but there are times where you want to see those two reflections as well. So our two examples, actually there's going to be more than two, but the ones that are on the board right now, we have again just a basic polynomial. We have one independent variable and all of those exponents are positive integers. And when we plug in the opposite of x, let me go ahead and this time write this as function notation. Just to give you a different look there. And we have f of negative x is equal to negative x cubed plus 2 times negative x. And, you know, function notation, there are lots of times in mathematics when we're dealing with more than one equation where we'd like to have those equations named, those functions named. So that's now function f. And just recognizing that that function notation, like in this case f of x, is a replacement for y. And a negative times itself, negative 1 times negative 1 is positive 1 times negative 1 again is negative x cubed. And negative or positive 2 times negative 1 is going to be negative 2x. Okay, now this notation here, this function notation, opposite numbers in, opposite numbers out. Well, with multiplication, you can create an opposite number by simply multiplying by negative 1. And if I take this equation and multiply through negative 1, I would get negative x cubed minus 2x. So with polynomials, not true with all functions, but with polynomials, if you see all those signs change, every single sign of each of these terms, if they all change, then you are looking at an opposite expression. And thus, this is an odd, where's my orange chalk at? This is an odd function. Now moving on to y is equal to sine of x, or let's call this g of x is equal to sine of x. Again, if you are just starting on your journey of algebra, you haven't dealt with your trig functions yet, you might want to just make sure your calculator is in degree mode and test a few values with your calculator. If you know the unit circle, use that. If you know the graph of these trig functions, well then you're set and go, and you're probably already on to the next question. So let's see what g of negative 30 degrees is. Well, that's going to be the sine of negative 30. The sine of negative 30 degrees is going to be equal to negative 0.5 or negative 1/2. And g of positive 30 now the sine of 30 degrees is going to give us positive 1/2. And indeed we have, that even hurt my ears. Sorry about that if you're listening to on the headphones. We plugged in our opposite numbers and got opposite answers. So now one test point, you know, for a function to be even or odd, this symmetry has to exist for every single point in existence, like an infinite number of pairs of points, opposite points. So you might want to check this a couple, 2-3 times. This certainly, we don't want to do a proof of you know, trying to show this in general terms really, other than to say that the sine of negative x is equal to the negative or the opposite of the sine of x. This does indeed come out to be an odd function as well. I would suggest that you, again, test more than just one point or a pair of opposite numbers before you come to that conclusion. And then if you have a graphing calculator, grab that as well and make sure that graphically it does look like you can take the calculator and turn it upside down and see, you know, the same, that it appears to be the graph is lining up on itself. You get the same picture. Okay, so we got a couple more examples. Let's get to those right now. Bam! For For our third example, we have f of x is equal to x times the square root of 1 minus x squared. Certainly not because of the radical in here. We don't have a basic polynomial function. Let's go ahead and plug in the opposite of x and see what happens. So we have f of negative x is equal to negative x times the square root of 1 minus the opposite of x, or negative x, we should say the opposite of x, squared, keeping that in parentheses. And we get negative x, or the opposite of x, times the square root of 1. Okay, so 1 what? Because, you know, we see that we have two negatives here. Are we going to let those two negatives cancel and create a positive? Or are we going to correctly apply the power of 2 first? See, if you let these two negatives just, you know, hit each other, see that they're side by side and go, oh, that's positive, well then you're doing multiplication before you apply an exponent, and that does not follow, of course, the PEMDAS, the order of operations. Please excuse my dear Aunt Sally, parentheses, exponents, multiplication and division. You know, those are on equal plane, whatever comes first, left to right, and then finally addition and subtraction. So negative 1 times negative 1 is positive 1, so this is going to be 1 minus x squared. Now let's look at how this equation compares to the original one. You know, all the signs didn't change, so maybe it's not odd. It's certainly not the exact same equation, so it's not even. So is it neither? Well, again, following the order of operations, when you take a number and you plug it in for x, and if I look at these two expressions and I see that they both have the same variable and I'm evaluating them at the same time, I'm going to be assuming, of course, that whatever x is representing is the same for both of these expressions. So something is getting squared. That same something's getting squared, and it's 1 minus that same something. So the expressions inside the square root symbol where you have to start working first are the same. And then working your way out of the grouping symbol, the square root symbol, we're going to have the square root of 1 minus x squared, the square root of 1 minus x squared, so they're equal so far. And then finally, whatever this answer is getting multiplied by x, and whatever this answer is getting multiplied by the same number but with a different sign. So actually, these are going to be what? Opposite answers. So this is an odd function. Next example. Example number 4 for identifying odd functions. We have f of x is equal to the absolute value of x plus 3 minus the absolute value of x minus 2. Again, the absolute value functions are a little bit tricky. They're not just basic grouping symbols. And again, these absolute value graphs will always have a sharp bend somewhere, and something is special happening with that. You know, that placement of that sharp bend with these absolute value functions are going to occur where the inside expression equals 0. But not thinking about that for at the moment and going, okay, well, I know that these are sort of a bit more complicated than many of the other types of functions that we deal with. I don't have a graphing utility to simply graph this to see if we have any symmetry to the origin. So I'm just going to plot some points. I'm just going to test some points, some opposite values. Well, f of 4 is equal to the absolute value of 4 plus 3 minus the absolute value of 4 minus 2. And that's going to be the absolute value of 7 minus the absolute value of 2. And, well, probably shouldn't be skipping steps. 7 minus 2 is equal to 5. All right? Well, let's try plugging in the opposite of 4. When I plug in the opposite of 4, which is negative 4, we get the absolute value of negative 4 plus 3 is the absolute value of negative 1. Again, there's two terms in here, so I'm not going to drop both of these negative signs and say that it's 4 plus 3 is 7. That is an incorrect statement. When you combine two numbers, well, assuming you're not multiplying, when you add two negative numbers or combining two numbers that both have the same sign, you want to add those numbers and keep the sign. So negative 4 minus 2 is going to be equal to negative 6. And the absolute value of negative 1 is 1. The absolute value of negative 6 is 6. And we get an answer of negative 5. So we plugged in opposite numbers and we got opposite answers. So this looks like it's an odd function. Great. It's not. That's why you need to test more than a couple of points if you can't work out the problem in general pure algebraic terms and your testing points. You can't do just one pair of opposite numbers. You need to do multiple sets to kind of be more sure of your answer, again, or use a graphing utility if you have it available. And also put a little bit of thought into it. Now, I mean, maybe we put some thought into this, but if we're going to try another couple of numbers, I'm not going to just pick them willy-nilly and just hope that, well, not hope, but just, well, I guess, yeah, hope I get the right answer. This expression, x plus 3, the sharp bends for absolute value functions occur when we can make the inside expression equal to 0. That's that x value that makes the inside equal to 0. That's where the sharp bend is going to be. Well, if I take that and I set the x plus 3 equal to 0, when I subtract both sides by 3, I get x equals negative 3. And when I set this equal to 0, I get x equals 2. I want to try, if you think about the negative 4 and positive 4, they were outside those values, and I got opposite numbers. So if I try negative 5 and positive 5, or negative 10 and positive 10, which are also outside those two x values, where the sharp bends of these absolute value functions, if you graph them separately, occur, then I'm probably going to get the same kind of answer. I want to try some opposite numbers that are inside this domain, if you will. Inside negative 2 and negative 3 and positive 2. So I'm going to try negative 1 and 1. So we have f of negative 1 is equal to the absolute value of negative 1 plus 3 minus the absolute value of negative 1 minus 2. And that's going to be negative 1 plus 3. When you combine numbers with different signs, you subtract and keep the sign of the largest number. So 3 minus 1 is 2 minus the absolute value. Like signs, so we're going to add those and keep the sign. And we get 2 minus the absolute value of negative 3 is positive 3. And we get an answer of negative 1. Now let's try the opposite of negative 1, which is positive 1. The absolute value of 1 plus 3 minus the absolute value of 1 minus 2. That's going to be 1 plus 3 is 4. Sorry, I kind of ran out of work. I don't like to work sideways. Minus the absolute value of 1 minus 2, which is negative 1. And now we get 4 minus the absolute value of negative 1 is 1. We just plugged in opposite numbers and did not get answers which were opposites. So this is neither even, it's neither even or odd. Which is, it's okay. There's nothing wrong with that function. And by the way, when I step off, I'll show you what I'll show you what the graph looks like on a graphing calculator. It just means it doesn't have symmetry to the y-axis, nor does it have symmetry to the origin. That's all. I got one more example. Bam! Last example. We got f of x is equal to x to the 4/3 power minus 4. And we're going to be looking to see if this is even or odd. Now, we've got a rational or fractional exponent. I'm not sure if you've had that in your studies yet or not. If you have, great. If you haven't, once you've been introduced to them, don't avoid them. They seem a little bit weird at first because you're used to square roots and radical symbols. But working with rational exponents really makes work when you have powers and roots together much, much simpler. But I am going to convert this into radical form just to let you see it both ways. So when you have a base to a fractional or rational exponent, the top number is power and the bottom number is your root. So you're looking at something that's being raised to the fourth power, and at the same time you are taking the third root of that value. And if you're doing it mental math, I usually tend to like to do the roots first and then apply the power. So x to the 4/3 power is the same as the third root, that's the index, of the third root of x to the 4th plus 4. Okay, so now we're going to apply this test. If I plug in opposite numbers, am I going to get opposite answers? I might get even the same answer, or, just find out that it's totally different. And thus it's neither even or odd. So f of negative x is equal to the cube root. Don't forget your parentheses again, of negative x to the 4th. Whoops, that's not a plus 4, that's a minus 4. Minus 4. And negative number, or the opposite of x, raised to an even number, which is 4, is going to cancel out those negatives, giving us the cube root of x to the 4th minus 4. So I said this was an example, the fifth example, dealing with testing for odd functions, but actually when we plugged in the opposite of x, raising it to that even power, we got an expression that was identical to what I was given in the first place. So actually what I've proven is that this is an even function. And this is the end of my last example. So, I'm Mr. Taru. Go do your homework.